This is Worksheet 5.6, Exercise 8. In Part A, we are told to use appropriate units and explain the meaning of this integral in terms of the car's motion. Since the derivative of the position function gives us the velocity function, the integral of v of t must be the position function s of t. We substitute the upper and lower limit into s of t, which gives us s of 60 minus s of 30. This is equal to the distance traveled in feet by the particle from t equals 30 to t equals 60 seconds. This is the answer to the first half of Part A. Keep in mind that this is a simplified approach to solving the problem to make it easier to understand. The integrand v of t is an absolute value because velocity is either positive or negative, while distance is not. Regardless of the sign, we want to know the magnitude of the velocity to determine the total distance. The same integral without the absolute value would mean the net distance traveled, which takes into account the signs of the velocities. For example, if the particle moves 5 units to the right and then 3 units to the left, this integral would calculate the net distance to be 2, because it moved 2 units to the right from its initial position. The integral from our problem with the absolute value does not consider the signs of the velocities, so it gives the total distance. For example, if the particle moves 5 units to the right and then 3 units to the left, the total distance traveled would be 8. Now we'll move on to the second half of Part A. Approximate this integral using a trapezoidal approximation with the 3 subintervals determined by the table. Now we have to solve this integral using a trapezoidal approximation. Think of this curve shown in this image as v of t, the velocity function. The graph is not to scale, but is solely used for your understanding. All negative v of t values here have been changed to positive because we are integrating the absolute value of v of t. Also keep in mind that the area of a trapezoid is the height times base 1 plus base 2 divided by 2. When doing trapezoidal approximation, each trapezoid's height is the change in x of that subinterval, and the two bases are the leftmost and rightmost y values of that subinterval. Think of it as a trapezoid that's rotated 90 degrees. So based on the data table, the subintervals from t equals 30 to t equals 60 are 30 to 35, 35 to 50, and 50 to 60. So starting from the first subinterval, 30 to 35, the two bases of the trapezoid are 14 and 10, not negative 14 and negative 10, because we are integrating the absolute value of v of t. We divide this by 2 and multiply 5 because in this interval t increased by 5. We do the same for the next two subintervals. The next subinterval is 35 to 50. The two bases of the trapezoid are 10 and 0. We multiply 15 because delta t is 15. In the next subinterval, 50 to 60, the two bases of the trapezoid is 0 and 10. We multiply 10 because delta t is 10. When we calculate this, the area comes out to be 185, which is the answer to Part A. In Part B, we are told to use appropriate units and explain the meaning of this integral in terms of the car's motion. And then we have to find the exact value of this integral. The derivative of the velocity function gives us the acceleration function. So integrating a of t should give us v of t. We substitute 30 and 0 into v of t respectively and find their difference. That would be v of 30 minus v of 0, which is the change in velocity from t equals 0 to t equals 30 seconds, because we are finding the difference in velocity at t equals 0 and t equals 30. That's the answer to the first half of part B. Now we have to solve for the exact value of the integral. In the data table, velocity at t equals 0 is negative 14, and the velocity at t equals 0 is negative 20. So this would be equal to negative 14 minus negative 20, which is equal to 6. This is the answer to the second half of part B. Be very sure to include the units. Part C. For t is between 0 and 60, must there be a time t when v of t is equal to negative 5? Justify your answer. According to the intermediate value theorem, if a function f of x is continuous in the closed interval a to b, then the function encompasses any value between f of a and f of b. Earlier, we were told in the problem that v of t is a continuous function. Since velocity is negative 20 at t equals 0, and the velocity is 10 at t equals 60, we know for sure that at some time t, velocity is negative 5, because negative 5 lies between negative 20 and 10. If a function is continuous over an interval, that means there are no holes or vertical asymptotes, so any y value in that interval must exist at some point. Therefore, the answer to part C is yes, the IVT states that since v of t is continuous in the closed interval 0 to 60, and v of 0 is negative 20 and v of 60 is 10, there exists a value t where v of t is negative 5. Now we will move on to part D. For t is greater than 0 and less than 60, must there be a time t when a of t is equal to 0? Justify your answer. In this question, we can't really tell if a of t is ever 0 just by looking at the values for a of t. So we will take a look at v of t, the antiderivative of a of t. If we draw a rough sketch for the function of v of t, we see that it starts at negative 20, decreases to negative 30, and goes back up to negative 20 at t equals 25. Here we see a critical point, which means v prime t, or a of t, is equal to 0. And therefore we can conclude that there must be a time t in the interval t is greater than 0 and less than 25 when a of t is equal to 0. But keep in mind that we don't know the exact location of this critical point. We just know that it exists in this interval. This can be explained using Rolle's theorem, a special case of the mean value theorem, which basically states that if there are 2 points in a function, f of a and f of b, which are equal, then there must exist a point between these two where f prime x is equal to 0. This is because if a function eventually comes back to the same point later, no matter what kind of path it takes, it must have a critical point in that interval. So in conclusion, our answer is yes, the mean value theorem guarantees a value t where a of t equals 0 in this interval.